Hi, everyone. Thanks for stay here for the last talk we have. My name is MJ. I'm from Meta. I work on the the batch compute team. Today, we're gonna talk about our journey about how do we migrate Java UDF to Velox use AI at scale. So we're gonna start with our the problem space, what's the problem we are solving, and then what's the tooling we are building for it, and then our end-to-end solution, and then share our current status and what's our next step. So we'll start with our the problem space. So as our previous talk mentioned, at Meta, we are migrating our Spark workload from JVM to Velox runtime through Guten. So ideally, you can see on the left side, everything just running on Velox native runtime, and until it hits the Java UDF, which Velox cannot run. What Guten does in this situation is fall back the unsupported Java UDFs back to the JVM on the right side, and then get the result back to the native until the UDF finish. It turns out this is one of the biggest blocker for us to fully utilize the performance win from the Velox runtimes in many ways. For example, the data conversion between native and the Java runtime is very expensive. And also with the fallback, we lost lots of the optimizations on the native side. And also, this also complicates the memory management on both JVM and the native side. In addition to that, what complicates the situation more is that at Meta, we have more than thousands of the Java UDFs and more than 60, around the 700 of this UDF. We don't have any of the Velox equivalents. We only have the Java coders. So this is a huge number of the unsupported Java UDF we have. So how can we tackle these problems? So initially, we just try to manually rewrite this UDF. We read the Java code and then manually rewrite in C++. It takes weeks, even longer, to migrate even one UDFs. And also lots of time, we misses lots of the edge cases because there's no documents and no unit tests for that. And also, since the volume is huge, 700 UDFs, so it cannot scale. So what we do next, as the AI is getting more powerful, so it's very naturally to ask, so can we just use AI? So can we just ask AI, read the Java code and rewrite everything into C++? So I believe many of you guys already tried this method, but however, it still doesn't work very well because AI is very good at reading source code very fast and generates boilerplate C++ code instantly. But lots of time, AI is not very good at catching many edge cases, and also AI cannot verify its own work objectively. So here is some the real example we hit when we migrate some of the Java UDF. And for example, for one of the UDF which expecting two the key value arrays. So the test cases here is provide two arrays with different size. So from the Java UDF, what I expect is we just ignore the additional values. So we just provide the two key value pairs. But when AI writes the Velox UDFs, it expect the key value has to be the same size, and then it's through the exceptions. So say the arrays doesn't match. So this is AI misses the edge cases. So another example is the same UDF, and then there is a null in the middle of the key arrays. So the Java UDFs just expect to throw exceptions because it doesn't allow null in the key, the map key arrays, but the AI just assume, just skip the null and just keep the rest of the key values. So those edge cases, the AI is not really good at it. So it's come from all this experience, our key insight is AI is very powerful, but it needs a self-verification harness to verify and validate its own work. So in our case, how can we provide the AI a tool to verify its own work? So the idea is very simple. Since the Java UDF can always produce the the expected results for any given inputs. So why can we just ask AI to always compare its results with the result from the Java UDFs? So with these basic ideas, it comes to our the tool we specifically built for AI agent for this purpose. So we call this tool the fuzz testing framework. So to make this tool AI native and AI friendly, we make a few design decisions. First, we need to provide AI agents ground truth by using the result from the Java UDFs. And also, the tool needs to be very lightweight. So everything needs to be run locally within single process. So the AI agent can very easy to run it with one command and on the same host and get back the result instantly. And also the tool need to be fast. So our tool right now can validate thousands of random inputs data in seconds. So the AI can just get fast feedback and iterate on the results. The last one is whenever there's a result mismatch, we need to provide the context-rich information so AI can know exactly the issue is and go back to reread the source code and fix the bug. So this is a high-level picture of the workflow of our tools. So we have the AI generates C UDF and the original Java UDFs in place on the right-hand side. And the AI agent will just use one command. We use bug test, which is our build, the build tools, the CMake, to trigger the tools in the middle to validate the results. And the tool will provide a signal of either pass or fail on the right side. So if it fails, a more detailed reports will just print it out. And the AI can just read out from the tool, and then AI can iterate and loop on it until the signal get passed. So if we look into the fuzz testing framework, it's on the high level on the top, we leverage the Velox vector fuzzer to produce randomized inputs with different data types, nulls, and the different encodings. And on the left side, we run the new AI generates C UDF directly with the random input data. And on the right side, we run the Java UDF with the same input through JNI. So there is no external cluster, external bar job. So everything just through JNI within this same process. And on the bottom, we have the comparators, which will collect the data, the result from both Velox side and the Java side to compare everything. The values, the exception behaviors, the nulls, all kinds of the results, and provide the validation signals. Next, I will hand over to my colleague Sandeep to introduce how do we leverage this tool to build our end-to-end solutions based on the AIs.
Thanks, MJ. Before I jump into the solution, so the first testing framework for sure is key to ensuring the correctness of the migrator UDFs, and it also provides that high confidence. But on its own, it's just another tool, and it needs someone to drive it. And to scale the UDF migration, we needed a system that can wrap the code generation and run it through the first testing framework, and that ends up being a single automated loop. And the solution that we have is this AI pipeline. It kind of starts with this touch point where the user prompts it to migrate a UDF, and it responds by kicking off this discovery and classification phase before writing any piece of code. It looks at the prod query plans. It looks at the Java UDF references to figure out the type of UDF. It could be a scalar or an aggregate function or a Spark expression. Once that is done, it also determines the migration path. So in some cases, it helps to avoid duplication. For instance, it might find that an equivalent UDF exists on the Presto side, And in that case, it ends up using a simple registration path instead of a full-blown migration. Once the discovery phase is done, it enters the generation phase. And this is where a lot of the AI heavy lifting happens and bulk of the migration work happens. So we know that AI is so good at reading the code, understanding the semantics, and then outputting new code. In this case, provided that you have the Java reference, the Hive UDF, and once you combine that with the linters and the code style guides, it's able to generate pretty good code. It also generates as part of the generation, it also does generates the first test and hands it over to stage 3. That's where the first testing framework kicks in and runs thousands of iterations of first test. If it finds issues, it sends them back to the generate phase where the patching is done. And that process repeats until the comparator says that everything is good. Stage 2 and 3 is currently implemented using a Ralph loop, and it perfectly fits the current model of TDD cycle that you just saw. Once everything looks good with the first stage, it moves to the shadow test. So that's where this is probably like the longest running stage we have. It picks the candidates from production and it runs them on the new and the old code path. And it also has the hash validation built in, so it ensures code correctness for the migrator UDF. Yeah, once everything looks there, it moves on to the verify and submit phase. So this is key. Like we have this case where the shadow runs fine, and maybe once you look in, you see that there was a fallback to JVM. So the verification looks into the shadow runs, digs into the tester runs and the executed plan, and makes sure there was no JVM fallback. So it basically looks at the executed plan and looks for the presence of Velox columnar to row operator and the relative ordering of the UDF execution. Yep, so at this point, everything looks good. It creates this, it autofills the diff plan, test plan, and creates the diff for review. So looking at how we got here, this was all before AI, right? We started out manual, all the phases of discovery, code generation, and the verification all were done by hand, and obviously it didn't scale well. And then once we had AI in picture, that's when things started moving fast. We were able to delegate a lot of the volume work to AI in the form of AI prompts and instructions, and that kind of helped speed up the migration. But it also came up with the challenges of you have to repeat the AI instructions, and sometimes you miss certain stages, and you end up having inconsistent diffs. And the learnings from this state led to the current state where we have now codified a lot of this AI instructions and prompts into skills, commands, and we also wrap them into an orchestrator, which can then pick up the task and run with it. Still have the touch points. The engineer has to kick off the migration, then there is a checkpoint confirmation, and obviously someone has to review the diff. Coming to the results, we see a tremendous increase in speed of UDF migration, going from a few weeks per UDF to under a day on the UDF right now. And at the same time, the correctness verified through the first testing framework and the shadow test. In terms of challenges, non-deterministic UDFs and formatting variations. I think this was covered in previous sessions as well. Like you have floating point number representation, differences between Java and C++, which kind of limits this framework. And we also have table type functions which are not currently supported by Gluten remains a limitation as well. What's next? Yeah, so we want to try to fully automate the UDF migration process. So this more looks like almost no touch points. And this means you have an auxiliary pipeline that kind of looks into the production usage, finds the unmigrated UDFs, and then kicks off the AI pipeline, which we have in place right now. And at that point, the only involvement comes in the form of diff reviews. Yeah, so that's the goal we have. Yep, that's it. Thank you.
I'm going to keep this short and sweet. I know it's been a long 2 days. So thank you, everybody, for sticking through all the way to the end of day 2. I know there were so many sessions this year. Everything's recorded. Everything's on live stream now, accessible. But this is really great. We do these things to get the community together. And of course, it's great to get all the content, but more importantly, to make connections with each other. So thank you. Make sure you're following Velox on LinkedIn, join the Slack channel, contribute to the project, and keep an eye out for VeloxCon Europe, VeloxCon China, and then hopefully next year's VeloxCon. Thank you all.